Imagine witnessing the same star explode twice in the same galaxy, but at different times. Sounds impossible, right? Well, not if you have a powerful telescope like the James Webb Space Telescope, and a cosmic phenomenon called gravitational lensing. In this video, we will explore the amazing discovery of the second supernova in MRG M0138, a distant galaxy that is warped and magnified by a massive cluster of galaxies. This is the first time that two supernovae were found in the same lensed galaxy, and they have a fascinating connection. They are both named Requiem, and they are both crucial for measuring the expansion rate of the universe, one of the biggest mysteries in cosmology. How did Webb detect the second supernova? How does it compare with the first one observed by Hubble? And what does it mean for our understanding of the universe? Stay tuned to find out. One of the galaxies that Webb has been observing is MRG M0138, a galaxy that is about 10 billion light-years away from us. This galaxy is gravitationally lensed by a massive cluster of galaxies named MAX J0138, which is about 4 billion light-years away. The cluster acts as a giant magnifying glass, creating 4 images of MRG M0138 around it. These images are not identical because they have different orientations, magnifications, and time delays. This means that the light from each image took a different path and time to reach us, depending on how much it was bent by the cluster's gravity. In November 2023, Webb detected a bright spot in one of the images of this galaxy. This spot was not there before, and it turned out to be a supernova, which is a massive explosion of a dying star. Supernovae are among the most energetic and luminous events in the universe, and they can outshine entire galaxies for a brief period of time. But this was not the first time that a supernova was seen in this galaxy. In 2016, the Hubble Space Telescope, which is Webb's predecessor and companion, detected a supernova in another image of the same galaxy. This supernova was dubbed Requiem. But what if I told you that the second supernova that Webb detected is also Requiem? How is that possible? Well, remember the time delay that I mentioned earlier? Because of the gravitational lensing effect, the light from different images of the same galaxy can arrive at different times. So, the second supernova that Webb detected is actually the same supernova that Hubble detected, but in a different image of the galaxy, and with a time delay of 7 years. This means that we are seeing the same star explode twice, but at different times, thanks to the cosmic mirage created by the cluster. Isn't that amazing? Now that we know that the second supernova that Webb detected is the same as the first one that Hubble detected, we can compare the two observations and see what they tell us about the nature and type of the supernova. As you know, Webb and Hubble have different wavelengths and sensitivities, and they complement each other in observing the supernovae. The brightness of the supernovae, as seen by Webb and Hubble, can tell us how far away they are and how much they are magnified by the cluster. It depends on the intrinsic luminosity of the supernova, which is how much light it emits, and the apparent magnitude, which is how bright it appears to us. The intrinsic luminosity of the supernova is related to the mass and composition of the star that exploded, and the apparent magnitude is affected by the distance and the lensing effect. By measuring the brightness of the supernova in different images of the galaxy, we can estimate the distance and the magnification of each image and compare them with each other. Also, the color and the spectra of the supernovae can tell us what kind of supernova they are and what elements they produce. And they depend on the temperature and the chemical composition of the supernova, which are determined by the type and the stage of the explosion. There are two main types of supernovae, Type 1 and Type 2. Type 1 supernovae occur when a white dwarf, which is the remnant of a low-mass star, accretes matter from a companion star, or merges with another white dwarf, and reaches a critical mass that triggers a thermonuclear explosion. Type 2. Supernovae occur when a massive star runs out of fuel and collapses under its own gravity, creating a shock wave that blows up the outer layers of the star. Type 1 supernovae are usually brighter and whiter than Type 2 supernovae, and they have different spectral features, such as the presence or absence of hydrogen lines. By analyzing the color and the spectra of the supernovae, We can identify the type and the subtype of the supernova, and the elements that it synthesizes, such as iron, nickel, oxygen, and carbon. However, analyzing the supernova data is not easy, because there are many challenges and uncertainties involved. For example, the lensing effect can distort and stretch the shape and the size of the supernovae, making them harder to measure and compare. The time delay can also introduce errors and biases, because the supernova can change over time, and the background galaxy can also vary in brightness and color. Moreover, the dust and the gas in the cluster and the galaxy can obscure and dim the light of the supernovae, making them less visible and redder. This effect is called dust extinction, and it can affect the brightness, the color, and the spectra of the supernova. To overcome these difficulties, we need to use sophisticated models and simulations, and correct for the lensing, the time delay, and the dust extinction effects. So, why is observing the supernovae in this galaxy so important for cosmology? Well, because they can help us measure the Hubble constant, which is a key parameter that describes the expansion rate of the universe. The Hubble constant tells us how fast the universe is expanding and how old it is. It also affects our understanding of the origin and the fate of the universe, and the nature of the dark energy that drives the acceleration of the expansion. However, there is a problem. Different methods of measuring the Hubble constant give different results, and they do not agree with each other. This is called the Hubble constant tension, and it poses a challenge for the standard model of cosmology, which is based on the assumption that the universe is homogeneous and isotropic, meaning that it looks the same in all directions and locations. One of the methods of measuring the Hubble constant is based on the cosmic microwave background, or CMB, which is the oldest and most distant light in the universe, emitted about 380,000 years after the Big Bang. It is a snapshot of the early universe, and it contains tiny fluctuations in temperature and density that reflect the initial conditions of the universe. By analyzing these fluctuations, we can infer the properties of the universe, such as its geometry, composition, and expansion rate. This method gives a value of the Hubble constant of about 67 kilometers per second per megaparsec, which means that the universe is expanding by 67 kilometers per second for every 3.26 million light-years of distance. Another method of measuring the Hubble constant is based on the cosmic distance ladder, which is a series of steps that use different types of objects, such as stars, galaxies, and supernovae, to measure the distances to nearby and faraway objects in the universe. It relies on the concept of standard candles, which are objects that have a known intrinsic luminosity, and can be used to estimate their distance by comparing their apparent magnitude. One of the most reliable standard candles are Type 1a supernovae, which have a consistent and predictable luminosity and can be seen across the universe. This method gives a value of the Hubble constant of about 74 kilometers per second per megaparsec, which is higher than the CMB method. So, how can this particular supernovae help us measure the Hubble constant and possibly resolve the tension between the CMB and the cosmic distance ladder methods? Well, this supernovae can be used as a new type of standard candle, which does not depend on the cosmic distance ladder, but on the gravitational lensing effect and the time delay. This method is called time delay cosmography, and it works like this. By measuring the brightness and the spectra of the supernovae in different images of the galaxy, we can determine their intrinsic luminosity and their type. Then, by measuring the time delay between the supernovae in different images, we can calculate the distance to the lensing cluster, using the theory of general relativity. Finally, by measuring the redshift of the supernovae and the cluster, we can estimate the expansion rate of the universe, and hence the Hubble constant. This method is independent of the cosmic distance ladder, and it only relies on the physics of gravity and light. However, this method is not perfect, and it has its own challenges and limitations. For example, the time delay measurement is not very precise because it depends on the accuracy of the supernova detection and the background galaxy variability. The lensing model is also not very accurate because it depends on the mass distribution and the shape of the cluster, which are not well known. Moreover, the number of supernova in lensed galaxies is very small, and they are very rare and hard to find. To improve this method, we need more data and observations from Webb and other telescopes, and more sophisticated models and simulations of the lensing effect. Thank you for watching this video, and I hope you enjoyed it and learned something new. If you did, please give it a thumbs up and leave a comment below. What do you think of the second supernova in MRGM 0138? How do you think we can measure the Hubble constant more accurately? And what other topics would you like me to cover in the future? Let me know in the comments, and don't forget to subscribe to my channel for more videos like this. See you next time.